So welcome everyone to the CITA seminar. It is a pleasure today to have Matt Orr visiting us from CCA at the Flatiron Institute. So he earned his PhD at Caltech in 2019, and then he went to do a postdoc at the Rutgers University. And then in 2021, he became joining appointment by the CCA. So he's an expert in cosmological simulations, in particular in the interstellar medium and its connection with stellar formation and stellar feedback. So please take it away.
Wow. Well, thank you for having me out here. I've never been to Toronto before, by extension, never been to CITA, but it's fun to be here. So anyways, I'm here to talk to you today a bit about kind of really just my chain of thoughts of star formation, low efficiency of star formation, the connection between feedback and turbulence in at late times, disk galaxies, the Fire 2 galaxies, and then thinking at earlier times, the proto-galaxies that turn into those, and trying to understand the transformation from pre-disk galaxies to disk galaxies and what's going on in terms of star formation and stellar feedback. So without further ado, I'll show a movie that definitely won't work on Zoom. So here is a kind of okay animation. It looks a lot better on the laptop of SDSS-3. And when you look out into the universe in your SDSS eyes, and all you see everywhere is galaxies. You see the large scale structure of the universe, but you see it in galaxies everywhere. And so if anything, this is the kind of thing that convinced me that the universe is just galaxies, and I shouldn't personally care about dark matter or anything but galaxies and what's going on in them. So without further ado, I would say that my big question is, how are galaxies made? Now, that might be a little bit of a red herring, because really the question that I have and want to share with you today is, how do stars form and what do they do? Because how galaxies are made really is just the story of star formation, I think, because after all, the definition of galaxy is just a whole bunch of stars in one place. We later figured out there's dark matter and all sorts of other stuff, but really it's stars. So this is prescient, or quite prescient, because like we have the decadal just came out somewhat recently, and as one of the big thrusts of the decadal is trying to understand how gas gets into, out of, around, processed in galaxies, and sort of understanding the drivers of galaxy growth is one of the big thrusts of the 2020 decadal. And even further within that is thinking about what's going on in terms of the baryon cycle of all your atoms and molecules, and what fun nonsense goes on between the interstellar medium, the CGM, stars, and other compact objects and the like. I really focus a lot of my time thinking about this aspect of it. Jets and winds, they're fun, but I really want to talk today about the impacts of what supernovas are doing in galaxies, interstellar turbulence, etc. So where did this all start? The recently late Martin Schmidt really kind of kicked things off in the late 50s, thinking about, well, how, if we have a scale height of young stars in our own Milky Way, does that tell us something about the rate of star formation? If we want to try to say something about this new interstellar gas that's being discovered with radio telescopes, etc., do we have some way to estimate what the stellar scale height in the galaxy demands in terms of how volumetrically stars are being turned into gas? And this was, going on, I can do math, 60 years ago, more, that we first really kind of thought about the rate of star formation. And add some time to this, and we got something that we now call the Koenig-Schmidt relation, where we want to talk about the surface density of gas in galaxies and the rate at which that fuel for star formation is being processed into stars. And so the rate of star formation, thus you would expect in some naive sense, must be related to the rate at which stuff is converted into star, or the stuff in galaxies is related to the rate at which it's turned into it. And this has been a cottage industry now for at least 30 years, since the 90s. And we have gotten to the point where we're no longer talking about just what's the rate of star formation in the galaxy as a whole, but we're really kind of drilling down, at least post when we started putting more than one pixel in telescopes to try to do this, post the late 2000s, talking about what's going on inside of galaxies on the the kiloparsec scale and below. And we're really trying to answer the question of how are patches of gas, or GMCs themselves, turning into stars, and what's the nonsense of business going on between those newly formed stellar associations and their parent birth clouds, and does that figure into the rate at which we see it going? And there's at this point there is some controversy, and still is to some extent, between, in the early universe, was star formation far more efficient? Was there something weird about it? Do we not understand XCO and the way we convert observationally our tracers of gas into gas surface densities, or similarly, what we think are tracers of star formation into star formation rates. So high redshift universe, there's certainly questions about what is the rate of star formation. Are we really seeing what we think? And in the local universe, talking about what's going on in the outskirts of galaxies, where we're dominated by atomic gas and its H1 observations primarily, or the sort of the suburbs and the inner core of galaxies, where you're progressively more dominated by molecular gas. And so one of the things that across the board, though, again with the exception of maybe the very early universe or crazy starbursts, star formation in galaxies appears to be quite inefficient. That on hundreds of mega-year timescales, on dynamical timescales of these galaxies, that at most 10% of gas is being turned into stars. Of the available gas we see in these galaxies is being turned into stars. And so this is really where this whole idea that star formation must somehow be inefficient is coming from. Now, what slows down star formation? Now, you might have another opinion, but I'm going to talk today about how feedback does all of it. So again, there are many modes of feedback in terms of what people might call feedback. There's stellar winds, there's radiation pressure, photoionization, there's supernova. That's a big one. And then, of course, there's AGN. I will not be talking about this because this is not primarily what I'm thinking about. But when you think about the galaxy mass function, when you think about how we're not turning all of our baryons into stars in terms of what we think of what halos are doing, at the high end, at the big massive end, probably AGN quenching galaxies, turning off star formation, really preventing that fire from continuing. And then at the low mass end, these processes are all relatively quite strong compared to the depth of the potential of a small dwarf galaxy. And so you might expect that if you set off 1 million supernova in the LMC, that it might explode, or the SMC certainly. But around the Milky Way, these things kind of are maybe very well balanced with how star formation is proceeding. And I want to talk about that. So I primarily work with a combination of the fire simulations. You have one of the fine fire folks upstairs. I've been told he's at a defense, so he can't be down here. Norm Murray has worked extensively with us. But thinking about simulations in the context of trying to understand on a single galaxy, or maybe a couple galaxies in a simulation box, how their baryons are being processed through cosmic time. And I've worked with a combination of this and some pen and paper theory as my sort of wheelhouse for the last, since I started going to grad school and got tricked into this whole business. No, I didn't. I chose willingly to do astronomy. So the fire simulations at this point go back the better part of a decade. And we've gone from Fire 1, Fire 2, and now we're coming out with Fire 3, which have all been sort of revisions on the feedback physics included and the numerics. And as we've pushed to higher resolutions, sort of understanding the coupling between these and the hydrodynamics, and now the magnetohydrodynamics. And so these simulations themselves are the ones I'm going to talk mostly about. I'm going to be focusing on the Milky Way mass suite of simulations in the Fire 2 wheelhouse. Fire 3 is sort of very actively being developed right now, where we're talking about 10 to the 12 halos that have resolutions of 8,000, 7,000 solar masses per particle. And these have that whole gamut of feedback processes, except for AGN, the ones I'm talking about. So stellar winds, radiation pressure, supernova, type 1 and type 2. And the resolution is such that we are resolving the ISM so we can talk meaningfully about a multi-phase ISM. And that's a very important and critical part.
Can I just add, I should know this, but exactly what is the difference between Gizmo and Gadget? They're both particle based, but
so Gizmo is built on top of Gadget. And if Gizmo, or if Gadget was SPH, Gizmo now was built with the meshless finite mass and meshless finite volume modes as well. So it's Phil's refinements on Gadget 2 and thus branching it off into its own thing. It doesn't stand for anything. He just thought it sounded funny that Gizmo would come out of Gadget. So that's primarily.
But okay, so it's basically the full SPH play that's laid out in the simulation.
Yeah, it's sort of the base, the code stuff. Yeah. And then fire specifically are all the physics modules on top of it. So within fire, or really any simulation, you have to pick any simulation with star formation, you have to pick some set of rules to how you're going to turn gas elements, particles into stars. So in fire, the checklist goes as you have gas. Well, it has to be gas. It has to be dense. In fire 1, it was per 100 per cc. In fire 2, the sort of fiducial density threshold ended up being 1,000 per cc, and this really was a consequence of our resolution. But here, we're able to resolve a few thousand per cc, so we're down to 1,000. It has to be molecular in nature, and for us, we're using the Krumholtz empirical fitting functions for essentially it's a column density, a metallicity dependent column density cut. And then finally, they have to be locally gravitationally bound. So the local velocity field, the local mass field has to be such that the gas particle, ought to be collapsing in some sense. If you meet all these criteria, then locally at the gas element level, you're 100% efficient per your local free fall time. So again, this is at the very base level of the code. It says, well, if a gas particle can collapse, 100% of that gas particle can turn into stars on its own free fall time. Now, for these galaxies as a whole, they end up being inefficient. And so the name of the game is, how do we take something that goes from being locally quite efficient to locally inefficient? And again, simulations have gone in the last, when I first wrote this text in the last 25 years, from the early 90s, when we were really just trying to get galaxies to look anything near realistic, things that didn't just have incredibly razor thin disks and little just bullets of all the gas turned into stars before Redshift 2, to matching the sort of interior properties of galaxies. If the goalpost at first was just getting a galaxy mass function to look anything near realistic, and at this point now we're trying to fit spatially resolved observations on a more population level, things like fitting like the FANGS data set or just any really IFU survey. So again, this was fire 1 work, but trying to think about, okay, well, if our naive estimate is we're supposed to turn all the gas into stars in 100 million years or so, let's pick a number, roughly a dynamical time of the galaxies, but not entirely, it's not the dynamical time everywhere. Well, in fire 1, we weren't 100% efficient. Through feedback mechanisms, we were somewhere between, again, 100 million year timescales, 1% and tens of percent, or and maybe a couple of pixels, 100% per 100 million years efficiency. Now, if we scale this, however, by the local dynamical time, so here I've thrown omega in, which is just the local rotation velocity over r. So you might expect this is the local turnover time in a disk galaxy, but really it's the dynamical time. Then again, in fire, which is all the blue points, and I put a bunch of random observations from Emerald Green Silk in the background, we're a few percent efficient per orbital dynamical time, essentially. So we've gone in these simulations, or rather through the inclusion of things like stellar feedback, we got to the point where we're able to match the predictions from the observed set of galaxies that are having a couple percent of their gas per orbital time turning into stars. So again, in a galactic sense, these simulations are inefficient. So the real question is sort of how do we get here, and why might we expect this either theoretically or otherwise in any case? And so if we were to come up with some hand-wavy definition of an equilibrium model for this, and there are a number, this is just one way to write it down, you say, okay, well, I'm going to be balancing the momentum in these galaxies somehow. I want to balance it from the injection from young stars, the stellar winds, the radiation pressure, the supernova in the ISM writ large, again, talking on GMC or KPC scales, and then balancing it with the dissipation of that momentum through hydrodynamic processes, or escaping out of the galaxy, perhaps in outflows, but through the dissipation of that turbulence. Here's a very simple equation you could write down, where your rate of star formation, there's some yield of momentum per star formation surface density. And then on the other side, you have your mass of gas times some velocity dispersion, your momentum in gas, and then there's some time scale here, the dynamical time. And this already gives you a hand-wavy sense of why we might expect an inefficiency, because the momentum from individual simulations of supernova, et cetera, the momentum that you get out per supernova event is quite high. And the velocity dispersions in galaxies are quite low. It's maybe, if we rearrange this, it's tens of kilometers a second at most in quite dynamically hot disks, and velocity dispersion, or the characteristic momentum per supernova event, is quite high. Written in these units, it's a couple thousand kilometers a second. So right off the bat, you get a 1%-ish coefficient out here. Now, this is obviously a very simple way of doing it, but more complex ways yield things like pi over square root of 2, et cetera. So order unity corrections, if you will. So if we were to go into fire and then start breaking up our galaxies on KPC patches and asking, well, are you, very star forming compared to that prediction, or not very star forming compared to that prediction? So observing the star formation rate in fire galaxies on KPC patches and comparing it against some prediction that you might put those order unity corrections in for, say the galaxy disk is hydrostatically supported, et cetera. You find immediately that there is a large amount of scatter. It does very well on average, which is heartening and is a good thing, because again, we've seen that our galaxies are a couple percent efficient, so it ought to go through the middle of this distribution. But there's a great deal of scatter around this prediction from something that looks at how sort of does this model work well when we're assuming things like hydrodynamic support, et cetera. And Alex Gurvich, who's a grad student with Claude-André Fauché-Giguère, did a very nice analysis of how well hydrostatically supported these galaxy disks are. And you see a 2 decks or so scatter for the majority of these galaxies. And that immediately says, well, okay, have I done a bad job either in my theoretical models? Is this just intrinsic scatter and I ought to not stay up too late at night or go out to the bars and try to think too hard about it? Is star formation just bursty? Always an answer. Tracers of star formation can tell us that these are short time scale events after all. Or have I just missed some physics? Again, I've done a bad job. I've written it down. I've gone home without including coefficients I ought to have. Now, again, fun hint of this was a project that I'd worked on thinking about where scatter in something like the star formation main sequence comes from in a population sense, where if you put the star formation rate of galaxies on one axis and their stellar mass on the other, in reality, we see some scatter about mean relation, scatter on the order of 0.3 or so decks, depending on who you ask. And these simulations at early times, redshift 1 and 2, et cetera, before their disks, jump all over the place in comparison to, well, the observed relation, but just in general to themselves. And sort of their raw star formation rates can jump around by factors of 100 in 100 megayears. And so really the burstiness of star formation, the time variance of it, is very evident here, and is, I think, one of the key things in terms of thinking about the evolution of individual star forming regions. And so if you are an atom in the ISM and you want to think about your own existence a little too hard, here's a fun way to frame your life, perhaps. And this is really how I frame my thinking surrounding what's going on in the ISM and the processes. So you might just be a gas particle in some kind of blob that some astronomer on Earth might call a GMC or a cloud, or maybe galactic cirrus, who knows? But at some point you become unstable, gravitationally unstable, and you begin collapsing. Now, again, I start with you become unstable first, because generally speaking, it's the loss of support that seems to come before, you don't have to become a molecule, or the ISM doesn't have to be very cold for it to become unstable. It just has to have enough mass in any given place for tumor instabilities, et cetera, to happen. At which point you become dense. You might make friends through astrochemical processes, thus becoming visible to people with ALMA. And at some point, new stars form. You've made enough friends, or you live in a dense enough neighborhood that you turn into a star. And if you are 1 to 3% of atoms in the ISM, you might join the star, which could be fun. Now, at some point, feedback is occurring and breaking these clouds up, dispersing the natal clouds. Typically, again, likely in the form of early feedback, prompt feedback, like radiation pressure and protostellar winds being the drivers of what's quenching, well, quenching is a dangerous word, what's stopping star formation in a cloud as opposed to the galaxy at large. And then supernova come around and ruin the thing for everyone after a couple million years. And then finally, at some point, the ISM, thus being a turbulent mess, is bringing these atoms back together and forming clouds once again, and the whole process starts over. And so the thing that I want to bring attention to in terms of framing this as a feedback problem to be answered is that for a lot of this cycle, turbulence is simply decaying. After all, if you're sitting around collapsing and cooling off and radiating away, all that's happening is energy is leaving the ISM in some sense. And then it through feedback processes, or there are things like accretion onto galaxies, bringing in energy from the CGM or radial migration. But turbulence is increasing when you've made stars and they're actively injecting their protostellar and early stellar feedback into their surrounding medium. And so, yes.
You discuss like turbulence decaying, but of course you've got self-gravitating systems, so that doesn't necessarily mean your velocity dispersion is going down, right? So are we? Just wanted to.
I would say in the self-gravitating regime, I would say you've kind of already lost in that you're on that power law tail of the ISMs.
Sorry, I didn't mean to interrupt you.
Oh, not at all. So I would say that at that point you've already lost in terms of you're no longer going to be in the large cascade of turbulence of the ISM. I think at that point, as soon as you are really, truly, honestly in a self-bound section, I agree that your velocity dispersions or the dispersions of like cores and things like that you see aren't going to be decreasing. But at that point, those things are no longer participating in the sort of, they're confined from the larger pressure of the ISM to themselves. And so at that point, those things are going to become, for the most part, without the injection of a lot of energy into like maybe the outer layers that are, real parameter of like 1.5, those things are going to become stars for the most part. That would be my defense, at least to that argument. No, absolutely. So again, there's this brief period where you have stars, but the ISM at large isn't, running up its turbulence. And that I think is an interesting thing, because if we frame this in terms of observed empirical scaling relations, things like Kennecott-Schmidt, this whole cycle, depending on, again, local density, average density, et cetera, might be observable as gas tracers. Certainly, H1 is probably visible in all of this, but you cap out at 8 to 10 solar masses per square parsec. CO is probably visible for a good fraction of it, but your star formation tracers are really only visible, again, from the moment you make young stars to some time scale thereafter, 4, 10, 40, maybe 100 million years. Well, I guess you see stars the whole time, so you can average that over a Hubble time if you want. But typically speaking, Kennecott-Schmidt is best approached on shorter time scales rather than Hubble times. So again, this is a fairly narrow window in terms of the ISM's life cycle, if you will, or rather Kennecott-Schmidt or any scaling relation is typically a narrow window in terms of where you're getting most of your useful information from on what's going on in the ISM. And spatially, this is also seen. People like Catherine Preckle, people in the room, et cetera, have looked at this sort of thing where if you're looking where your tracers of star formation are and your tracers of gas properties, your GMCs, et cetera, they're not necessarily co-spatially on top of each other one-to-one. Usually close by because, well, they all live in the galaxy. But they aren't on top of each other like you might expect. And this tells us something about the timescales and the evolution of these regions from gas blobs to blobs of young stars. And so, again, given this time evolution and spatial evolution, you might go and try to write down, simple ODEs because you're a grad student and you want to have a simple model that tries to explain something, where we might try to think about how this turbulent momentum evolves. And so if we let this little sigma evolve and we just use a simple framework for trying to do so, you might try to work on source terms in terms of some delayed function that's taking into account star formation that occurred some time ago and some constant dissipation term, and write down an attempt at an ODE. Here's one. There's a delay term. There's this constant rundown term, and you get some yield of momentum per, and then you have, again, some prescription that says as a function of the instability of the ISM, you get a star formation rate, et cetera. But what you're really trying to do is ask some question about how can we evolve very simple in a semi-analytic fashion models, and does this give us an idea of the scatter that we might expect in terms of these timescales, et cetera? And maybe we could evolve that into spatially, but let's just stick to timescales right now. Say you have some patch of your galaxy, you take that ODE and you knock that galaxy, that little bit of the galaxy, by saying, okay, you're tumor unstable to start, let's see how you ring down. We can see immediately that, again, in that there's a native time scale. I'll jump back here, and that time scale being the dynamical time that you say turbulence is decaying over. And it appears in here where there's this ring down on dynamical times. And the interesting thing is, if you say that there's some response of the velocity dispersion to local instabilities, and then star formation is thus 180 degrees out of phase or something of this, you can get this scatter or a scatter that you might expect on a larger scale, on the scale of several kpc. And you get an idea that galaxies ought to be very difficult to keep in local equilibrium, because after all, the ISM either wants to be collapsing and cooling off and hanging out, or it's being punched in the face by young stars. And it's very hard to balance those things, again, on fairly small scales for any appreciable amount of time. And so if we go and try to plot expected scatters against something like Koenig-Schmidt, or in another plane, putting the velocity dispersion itself versus the star formation rate, we can plot this and compare it with some observational products, and some intuition starts to come out of this, where at low gas surface densities, well, the ISM in some sense doesn't have a high heat capacity, if you will, for carrying momentum. And so if you don't have very much gas, but you put 10 supernova off into it, well, that gas is going to respond quite strongly to it. Will be heated quite effectively in some dynamical sense. And so you might expect quite large variance in your star formation rates, because after all, the gas is either cooling off and turning into stars, or it's being very dramatically affected by its star formation and turning it off very well.
Are sigma gas and d sigma star dt measured in the same place?
In this model, yes. So these colored points are just integrating that ODE in the semi-analytic fashion. Oh, empirically, yes. So this is again averaging over KPC scales or so. They're measured in the same place.
Okay, that's what you were showing just now, a plot of GMCs and star formation zones in a real galaxy, I think, or maybe it was a simulated galaxy.
That one back there.
They weren't in the same place.
Okay. So that one, which I'll get to if I know how to function with this delay, right here. So again, I would say in this case, this is real data in M51. So I would say that in this case, I'm thinking about averaging over larger scales than necessarily just these individual points. And so thinking about KPC patches that are including multiple GMCs in some sense, as opposed to resolving out fully these clouds. Whereas at very high gas surface densities, there's a pretty good carrying capacity, if you will, for the momentum in the ISM. And so the ISM at high enough surface densities, if you're putting hundreds of solar masses per square parsec in an area, might well be quite close to equilibrium, at least in some sense that the star formation rate response won't be high. And so again, at low velocity dispersions or low gas surface densities, you might have a large run in your velocity, in your star formation rates, whereas this relation kind of could turn over as you go up from something like galactic outskirts towards, the suburbs and centers of galaxies, where.
Jump in again. Was your ODE stable in all the regimes you looked at? I mean, it was damping on a.
It was damping and stable in any physical regime. Anything where I picked numbers that galaxies could really have, it was stable. It was a couple years ago now, so I don't remember how I could break it. I could break it by putting in some numbers, but trying to remember if there was any regime that was like a real physical numbers. Yeah. But it was stable. So the ISM is, I think, fairly, it just wants to run down. I think if you included like some kind of thermal instabilities at some point, you just heat it and it never wants to cool on a Hubble time. But yeah, I already said these things. Anyways, so you could get some intuition for how you might expect the ISM to be responding to these in either low gas surface density or high gas surface density regimes. And so again, framing this whole thing as turbulence running up or down, or one way to think about it, we should, or I ought to now go and look in the fire galaxies and say, okay, well, can we look at these velocity dispersions and see to what extent did does this intuition that we've been trying to develop reflect reality, or not reality, but our fake simulated reality that comes close to looking very like reality in some Mach-Hubble images. So if we were to go into the Fire 2 simulations and start asking questions like, what's the velocity dispersion in all of the ISM and the H1 plus the H2, and that's with the Roman 2, not the, wait, no, the Arabic 2, not the Roman 2, just because I hate that we as a field decided that those are both H2. And then something like the cold and dense gas, the H, again, 2, we can see the velocity dispersions, again, match the core of the distributions match fairly well with observed IFU surveys. But we see something that's quite interesting. And again, reminiscent of thinking about how the velocity dispersions don't have to change all that much, but your star formation rates can. Where again, this axis, unlike much of astrophysics, is log, and this one's linear. And you can see that over 3 decks in star formation rates in these simulations, and in reality, the velocity dispersions don't change all that much. They change, factor of 2 at most on average. And so that is a very interesting question already of why is the ISM, really not all that responsive to the local conditions, or you might expect that there'd be a power law or something like that, as opposed to something that hardly seems to budge. It does increase that higher velocity dispersions do correlate with higher star formation rates, but that might also be just some effect of the centers of galaxies. Maybe these things aren't all that connected. As you're averaging over short time scales, again, this is 10 mega years, so H alpha-ish time scales versus 100 mega years, longer time scales, UV or some such thing. There is a bit of a response. And there is some kind of lower envelope where you can't really have very low velocity dispersions and very high star formation rates. You might have expected that you would see such things. Now, again, a lot of this thinking or what I've been talking about has been restricted to late times, thinking about spiral galaxies that are dynamically cooler, like our own Milky Way, where we might be able to generate this kind of intuition, thinking about how disks are processing hundreds of GMCs at a time into stars. But because of tens of billions of dollars spent by our community and the governments of the world, we're now going to be able to access the time when things like the Milky Way formed at KPC resolution. So the Milky Way are not formed, but it fell into kind of a disk configuration, if you will. And then again, peak star formation just in the universe is happening at earlier times on this. And we're finally pushing to the point where we're going to have sub-kiloparsec resolution, and it's meaningful to be talking about what not whole galaxies are doing in terms of processing their dust and gas into stars at these formative times, but as we've been talking about on the scale of the units of star formation in these galaxies, of the largest cloud structures and the largest meaningful blobs of gas. And so it's a very meaningful question now, is the ISM, does it behave quite differently at this time? Or is most of our intuition portable to this? And so I have been wanting to think about some of these plots I was just showing, but now looking at the evolution of these galaxies as they form from redshift 0 up to redshift 2. And so what I'll show now is, again, the velocity dispersion here. This is of the H1 plus the H2, trying to understand how the ISM, what you would call probably all participating in star formation, the neutral ISM, neutral molecular ISM, how its velocity is responding to star formation rate. So again, here it's the 10 million year star formation rate. And I've colored this by a number of physical quantities that you might think are important in galaxies in some sense. The fraction of gas that's in a very cold molecular phase of all the gas, the actual gas fractions, so fraction of gas to stars, some parameter tumor Q, the marginal gravitational stability of the gas, where if it's very blue, it's on average unstable and ought to be fragmenting and collapsing. And if it's red, it's probably exploding and not actually something you should think of as a stable ISM. And then I've tried to make some parameter of like a burst factor. You might think of this as the ratio between 10 million year star formation and 100 million year star formation. So blue is star bursting, red is star bursted gas.
You did this for Fire 1 or Fire 2.
This is Fire 2. No, not really.
Fire 1 is burstier.
Yes, it is, but on average, the behavior of the ISM isn't all that different. Again, on average. So there's more variance in Fire 1, Fire 2, the variances come down significantly.
And so that variance not manifested in this diagram?
Well, in the shape of the colors, if you will, like Fire 1, blue is still down here and red is still up here. Yeah, it has more scattered. It's more scattered to higher velocity dispersions in Fire 1, essentially. I guess there isn't that much scattered to lower.
To take a shot here, is this dispersion, does that soak up most of the variation in Fire 1 and Fire 2? So that it becomes like the second parameter?
I haven't thought of it that way.
It's really important for our issues here on line intensity.
Yeah, I haven't thought of it that way in terms of the main difference that you might see observationally between the two data sets. But I think in some broad sense, you could say that, because the underlying physics don't change all that much. Implementations of them do. But broadly, I think that could be a significant fraction of it. And then as the resolution has increased as well, the big difference of Fire 1 to Fire 2 is pretty much all the plots anyone shows you from Fire 1 is at 56,000 solar masses or so per particle. And then pretty much all the things people are showing you from Fire 2 are 7,100 solar masses. So some of that also is embedded in that, which allows for looking at a colder, dynamically colder ISM as well. So So again, the average doesn't change with the resolution. At least we're still in the regime for these galaxies, at least, where averaging over individual stellar populations, averaging of the IMF seems like it's on pretty solid ground. It's fairly well converged in terms of the global star formation rate, et cetera. The statistics of once you get really below KPC, the structure does change. For Fire 1 was clumpier and Fire 2 is less clumpy in some broad sense. So I would say that, again, the convergence is on the KPC scale and up in some sense in the average quantities. But what like velocity dispersions and such are below that have changed. So I would say, again, things that you're trying to ascribe to physical processes on galaxy scales, pretty solid ground. I'm not going to try to tell you very much about the dynamical state of the Fire 1 galaxies on the scale height and below, because I don't think it's super useful below like the scale height of the Fire 1 galaxies.
Feedback that actually made Fire 2 galaxies less bursty than Fire 1, or like change of hydro solver method also made Fire 2 less bursty comparing with Fire 1 galaxies?
I don't think it's a hydrodynamical model. I think if a big part of the jump from Fire 1 to Fire 2 was the supernova implementation and making sure that it was like isotropized correctly. I don't think it was as much to do with the hydrodynamical change, where we were primarily doing SPH to MFM from Fire 1 to Fire 2. I don't think that was the reason that the ISM, in some sense, is a little, I guess, more stable on average in Fire 2. Because, okay, here's an aside. There's a lot of statements about when we talk about galaxies that we're simulating. People say, oh, this simulation suite or that simulation suite, the feedback is too strong or too weak. That's I think a common phrasing that people try to use. I think as a field that that's a little bit misleading, because exactly as you had said, just about everyone, like everyone else, is putting on their pants one leg at a time. They're putting in 10 to 51 ergs per supernova and trying to see what happens if they can resolve the supernova themselves. So it's not necessarily a question of, did they put in too much or too little feedback? But it's a question of, is the ISM, which is really just demanding some amount of momentum in it to be stable, is that ISM more or less stable than you might otherwise expect? And I think certainly for Fire 2, the disks at late times, while again, a Milky Way person is going to say 30 kilometers a second, the high end of our, the meat of our distribution, that's really high for the Milky Way, which is true, but the Milky Way is a weird object in some sense. The Milky Way has a very dynamically cold gas disk. It's fairly well in line with the broader observations from something like SAMI, et cetera, that, disk galaxies are in the, low tens of kilometers a second velocity dispersion when you're talking about the full weight of the ISM. And so I think part of this is a question of us moving both observationally and our thinking to higher redshift to understand in a pre-disky configuration, should the galaxies be exploding the way that we see them, where they're the disorganized dispersion supported blobs that seem to always overshoot their star formation rates, et cetera. And is that reflected in reality? And I think we're getting a better idea of that with Webb observations. Yeah. Does that answer at least some of these questions? If not, I'm very happy to talk about this offline. I'm here through Thursday night. Getting back on the up train. So all these colors, what I'm just going to say between cold dense gas fraction, gas stability, starburst factor, you see a lot of intuition that you might expect. Things that have low velocity dispersions that maybe don't have enough turbulent support are generally, well, not very turbulently supported. They're dynamically unstable in some sense. Unstable things are star bursting in some sense. And then again, things that are very dynamically cold, locally, they're going to have high gas fractions, again, because if your whole gas disk is really cold, well, all the stars have a higher scale height. And so locally, the gas fractions are going to be higher. And then things that the gas is all spread out and or outflowing, well, they're going to be very, gas poor. And similarly, things that are, again, most star bursting are probably things that have a large fraction of molecular gas. Now, the only things that change when we try to think about these galaxies and their evolution in cosmic time, the velocity dispersions get higher across the board. The squiggles also get kind of, the squiggles in my lines get bigger because I went from like 30 snapshots to 10 snapshots because I was making this a couple months ago and I didn't want to do all the snapshots. And so I'm going to update it before this becomes a paper. So just try to smooth that a little bit with your eyes. But the coloring stays roughly the same, with the exception of the local or the sort of cold gas fraction. The ISM is warmer in galaxies at earlier times before they're dominated by their their cold molecular reservoir. So in fire, there's a higher fraction of warmer neutral gas than very colder neutral gas. But the intuition surrounding what's going on in these galaxies is much the same. Redshift 1, Redshift 2. Here again, these things are just gas blobs essentially, and they're fairly warm in terms of their total ISMs. But still, how the starbursts are working, how the instabilities in the ISM appear to arise on these KPC scales are much the same. And so I think that this is all to say that our intuition surrounding how the ISM ought to behave really shouldn't change all that much from early times to late times, or vice versa. And so when we're thinking of this nice plot that everyone sees everywhere because it is inextricably tied to the decadal at this point, of thinking about how gas gets into galaxies and is processing and being thrown out of them, you might at early times be replacing this nice disk galaxy with a blob. But still, I think our thinking really ought to be zooming down to, again, what's going on in terms of it's more turbulent, not very disky, there's outflows, but there's still these quanta of star formation in them. I swear to God, I'm coming in for a landing. I got some time, but we'll get there. So star formation is fundamentally clustered. And I know some people in the audience care deeply about this and know perhaps even more than I do about it, hopefully do. So what I want to talk about now is thinking of a model for this clustered feedback and how it ought to be related to a lot of these things we've just been talking about. Because before we were talking about star formation in some very smoothed out sense, where you have a smooth distribution of stars over KPC and a smooth distribution of supernova. That really belies kind of what's going on. That you make a star cluster on some scale, you're making a star cluster, which again, I've gotten lit up by audiences by this before. By star cluster, I mean a number of stars in roughly the same place and time formed all together. Not necessarily a formally like globular bound association, but a lot of stars all in one place. You make them all at the same time, Here's a nice simulation from Mike Rudich, my former office mate, good guy. That star cluster is going to start blowing a bubble, where its surroundings, the supernova starts to go off, and again, you make a bunch of stars in roughly 40 million years. All those stars that are going to go supernova do, and their shock waves, if it's a large enough cluster, will add up sort of additively around themselves and begin to form a shock front that grows. And as it grows, many people have shown that at some point the shock front is momentum conserving, and so you're really just sweeping out gas in a momentum conserving fashion. We can write down again simple ODEs, my favorite, or simple algebra in this case, which we then integrate, which makes them ODEs, right? Where you're just balancing the momentum of the bubble front with the momentum put out of supernova over time, and then at some point you run out of fuel and you've gotten all the momentum that you're ever going to get out. And these sorts of things are calibrated off of like the IMF, what the lowest mass star to go supernova would be, and then individual supernova shock front simulations to say how much.
If the momentum per unit mass comes from a set-off phase in a certain environment, but then you're putting that into the interior of a superbubble.
Yeah.
So do you have to adjust it to account for the environment in which those remnants?
Ought to or must need to. Thankfully, simulations of just this thing have shown that they add up mostly linearly, or it's very close to linear. That maybe they're doing a bad job, but it made my job easier. That it appears that maybe there's some funkiness there, but it's the sort of the late times result of once it's joined up to that shock front, it seems to linearly add to it in terms of roughly the same amount of momentum per supernova, which, somewhat surprising, I'd agree, because there's a lot of fun hydrodynamical processes going on inside of that. But regardless, you then could imagine there's really 4 outcomes, 2, but then you got another 2, where the galaxy is or the scale height of the gas is either small enough that the superbubble will grow and reach it and then break out, form some venting chimney where outflows or winds are able to be launched out of the galaxy, or the shock front was weak, there weren't enough supernova, or the turbulent pressure of the ISM was high enough that the shock front expanded until it came into pressure equilibrium, and then it fragments and stalls within the ISM. And then the bonus 2 cases are this happens either before or after you run out of supernova. You could imagine you have a coasting phase where it coasts and breaks out, or coasts and stalls and breaks apart, or it's a powered phase where the supernova keep going off into a stalling remnant, or keep going off and drive a wind. I'll tell you right now that it never seems like in the real universe it's probably coasting. It seems like it's always either powered fragmentation, powered stalling, or powered breakout. So these are some simulations from, again, a collaborator on this project, Drummond Fielding, who's looked quite extensively at this. He's another postdoc at the CCA and will begin a faculty job at Cornell in the fall. So simulations seem to bear this out, where we really do seem to see, and observationally you also see venting, supernova driven winds or bubbles in the ISM locally. So if we were to then put this out in a phase space that we seem to be able to derive from this, where on one axis is the local gas fraction. Again, we're painting this all on a roughly tumorous stable, right on the edge of stability ISM, versus your local dynamical time. You see this phase space that kind of comes into existence, where you have a coasting fragmentation phase, powered fragmentation or powered stall phase, a powered breakout where you're driving outflows or winds, and then a very narrow little sliver, at least when you adopt any sort of physically real parameters of coasting fragmentation. And so again, it doesn't seem like when you reveal, and it's actually omega and F gas, that the dynamical times of galaxies are never so long as to be able to support this coasting phase, that everything more or less in the real universe, where the ends of star forming disks, et cetera, appear to end, is in some sort of powered phase. And again, that was where that was. So I squinted and said, this kind of looks like the border between California and Nevada. So I call this the Lake Tahoe plot, and Las Vegas is there, which is great because that's where powered blowouts are happening. And that seems somehow thematically appropriate to Las Vegas. I've also made jokes about like Santa Barbara being very chill, but anyways, you can write down a power law, because everyone loves those, to explain this sort of edge ratio, where there's just some relationship between your dynamical time and local sort of parameters of your galaxy. which is fun. And if we try to go and steal tables from Adam Leroy's papers and then put galaxies on here in a resolved sense, where I have taken a bunch of local star forming galaxies, and in this case, there's like 7, because Chris Hayward said more look dumb. And then I bold some of the points, and those points are the ones where there are observed outflows from those annuli or the centers of those galaxies. We see that there's at least oh yeah, that kind of looks like it agrees with this theory, where the vast majority of star forming galaxies don't seem, and the regions within them seem to be containing their supernova on average. That for the most part, super bubbles are growing but fragmenting within their disks, or depositing the vast majority of their momentum within their disks, versus the centers of galaxies and the outskirts of some galaxies where the super bubbles are breaking out, driving winds, etc. And these, and then here's an attempt to try and understand where redshift 2 SMGs lie. These are the 2 simulations from Drummond Fielding from earlier, showing something picked to be very deeply in the breakout blowout phase, and something picked to be fragmenting and sputtering within a galaxy disk. And so these are some fun galaxies in here, like NGC 253 is here. There's tentative observations from the center of 4321. I'm an observer, or a theorist, not an observer, and so I don't really know all these phone numbers, but they're pretty galaxies. And so if you ask yourself, though, okay, if you're breaking out of the galaxy, where is that superbubble momentum going? And this is, again, I think, one of the primary questions about what's happening with clustered feedback. Well, if you break out of the galaxy, pretty much as soon as the bubble breaks open, every subsequent supernova thus has to have a clear shot out of the galaxy, or a much clearer shot out. And so if you break out really quickly, your superbubble reaches the edge of the galaxy in a couple million years. Well, you have like 30 million years of supernova going off that are just throwing their momentum out of the galaxy. So a very small fraction, or a much lower fraction of your momentum, ought to be contained or put directly back into your ISM, thus kind of making things a little unstable. Versus if you are taking 30 million years to break out of your ISM, where it takes a really long time for the bubble to grow and reach the edge of the gas disk, or the gas clump, well, most of your momentum will have been put into that shock front, put into the dense gas in your galaxy, thus containing a large fraction of it. And so this might be an interesting way of framing how, well, at early times, if galaxies have shorter or longer dynamical times because they don't have as deep potentials, etc., but very high gas fractions, well, they might be exploding messes, but that ISM is still absorbing most of the stellar feedback. Whereas at late times, as our dynamical times become shorter in the centers of galaxies, the gas fractions fall, you might really be supporting some kind of flip-flop behavior, where either you contain the superbubble and you're trying to be a real stable ISM, or it breaks out almost immediately from your galaxy center, and you drive the vast majority of your momentum into winds, something like you see with like M82. And in the Fire 2 galaxies, their centers specifically, I went and looked, this is a project with Kara Battersby at UConn, to try to think about how the centers of the Fire galaxies might look like the CMZ, the central molecular zone of the Milky Way, or not. We saw really 2 classes of galaxies where the galaxies either were like flip-flopping and just blowing out from the galaxy centers, or they were pretty stable. So they're, this is just like a hand wavy, like, maybe that kind of works. Filler slide. So, and then thinking to the future, and again, I'm going to wrap up now, that as these Fire galaxies are evolving, they're going from some regime where they're very gas rich, they're dispersion supported, but absorbing a lot of the momentum, evolving into a regime where the majority of where star formation is occurring is deeply embedded in the ISM. It might really give us an idea of why these galaxies are behaving slightly differently, but their ISMs, when you ask about your intuition of what's going on, is portable. It's roughly the same between low redshift and high redshift. So a project that I'm working on now is making mock observations of these that you might be able to see in rest frame. It would be rest frame UV, but James Webb will see it in their short filters. Where we're looking at where star clusters are forming and breaking out in sort of the spatial correlation between star clusters and the feedback and the gas and the ISM. So that's an ongoing project, and it's reminiscent. Future. Sorry, it's an hour of this. So anyways, in summary, I think it's very useful to be framing are thinking of what the ISM is doing in terms of some cycle where you're putting into the baryon cycle, you're putting in momentum. That momentum wants to run down through hydrodynamic processes. And the ISM is broadly some kind of stable or thing that wants to be in equilibrium, but it doesn't want to be in a static equilibrium, or rather it struggles to be, but it's in some kind of dynamical equilibrium. And low redshift disks might be a lot closer to a static equilibrium, if only because they're absorbing per star formation event, they're absorbing all that momentum for the most part, or they just let it all go. And at high redshift, these objects are being disrupted, but absorbing the momentum and falling apart. And so even though the ISM at low redshift and high redshift seems to look quite different, many of its dynamical properties seem to be shared in terms of where and when gas is dynamically unstable and forming stars, how feedback is being absorbed into the ISM or not. And so it's critical that we understand these feedback processes, understand the spatial correlations of star formation and feedback, and what happens when you have things like star clusters driving stellar winds versus turbulence within galaxies. So it's all going to be quite exciting. James Webb is going to help us really unveil some of this at high redshift in the rest frame UV. And I think that's going to be quite critical for our understanding of what young star clusters are doing to their surroundings. So again, I'm here through Thursday. Thank you very much for having me.
So questions?
So what's the mechanism by which gas is blown out of galaxies?
So again, in my framing of what supernova super bubble feedback is doing, is as the shock front sweeps up most of the gas, okay, it'll reach the edge of the gas clump or gas cloud, and okay, as the shock front hits it, there's going to be some kind of like cold cap that's thrown off. And simulations like Tigris or these tall box models typically show that there's a slow moving cold component that is kind of thrown off as feedback is trying to, or super star formation driven feedback is driving stuff out. That's kind of throwing fountaining material. And then there's a hot wind that follows, where it's subsequent supernova that never really are, entraining cold gas into it, or just shooting a hot, fast wind behind it. Most of the mass, I think it's about equal parts probably between that cold cap and the hot wind behind it, but most of the energy is all in the hot wind.
And at its peak,
Mhm.
what fraction of the mass falling in goes back out?
That falls in from like one of these feedback events, or just in accretion?
Cold flow, or that hasn't yet resided in the galaxy, inside the, I don't know, inside the scale radius of the galaxy, something like that.
Yeah.
At its peak, what fraction is going out?
Compared to what's going in. Well, for a lot of our simulations, like for the dwarf galaxies, we get mass loading factors of like 10, where you just have to throw out most of the mass that comes in.
Yeah.
For the Milky Way, L-star sized galaxies, it's much lower numbers. It's 1 to 3, and so it's kind of at some point it's trying to be in equilibrium with the amount of stuff that's throwing in, but it's slowly losing essentially. And then something else kicks in, like AGN, that really has to drive it back down.
So are you saying that, roughly speaking, when mass loading factor being the ratio of mass,
The mass in the winds.
mass from many stars, yeah.
Yeah.
When that ratio drops to unity, then that's when the AGN are taking over? Or is it still above unity when the AGN are taking over?
I don't have a clear answer, because the simulations I work with don't have the AGN. We just know they start looking quite wrong above Milky Way mass. And so it's unclear if the AGN should kind of like smoothly turn on as that ratio is falling, or if the AGN turn on for other unrelated reasons while the ratio is still high, and kind of then that ratio then just drops like a rock, because star formation, well, I guess star formation would be going up. Or no, star formation would be going down, but the number would be going out. So I don't think I have a clear answer from you, at least from the perspective of like fire. But subsequent simulations, Fire 3 will have, or do have AGN modules, and so that's definitely an area that's being explored.
Is Fire main in Fire 3 the AGN, or?
So again, Fire 3 specifically, I wouldn't say the AGN are like, they aren't standard in it, but I think maybe the way is we feel confident enough in the approach of a lot of the other processes that we're now exploring the AGN parameter space in Fire 3.
Fire 3 as well, or
There have been minor tweaks to a lot of the things, like the way that photoionization is done immediately around gas particles, or the gas particles around young stars. The way that supernova momentum is, making sure that there's no like boosts to the energy by accident by jumping into like the moving frame of the ejecta. Minor tweaks that, again, I would say on average things aren't changing, but like locally, dynamically things are. So like the
I mean, the examples you've given, you're just trying to, it sounds like the representation of the physics numerically, but are there any instances where you just don't have the resolution, you have to make a phenomenological adjustment to a parameter in the code?
well, in this case, the resolution hasn't changed between Fire 2 and Fire 3. And so there haven't been any changes like to any phenomenologically included things.
There are some.
I mean, for the black hole feedback, yeah, there's just no way that we'll ever like, so that's essentially entirely a black box phenomenological model of the inner 10 parsecs around whatever black hole particles. The star formation, I think we've gotten rid of the density threshold, for instance, because it didn't matter. It was the local velocity field. It was the local sort of the shear tensor that was the primary driver, and said, okay, we're gonna go with the velocity field and a local virial parameter as sort of the primary drivers. Yeah.
Okay.
So thank you. I have 3 questions. So first, do you think that this supernova feedback is the most effective?
It disrupts this molecular cloud before the supernova happens. So in that case, what I think is like
Radiation pressure or the stellar winds might be the most effective feedback to reduce the star formation.
do you think it is supernova?
So I guess the way I'll put it is the supernova are what's regulating star formation on the KPC scales in terms of what's becoming GMCs. What sort of where and how much gas is falling into the star forming phase. And then because it's prompt, those other processes, the radiation pressure, the stellar winds, et cetera, are the things that are disrupting that cloud. And that, so locally, if you have a gas cloud and you just have supernova, so you just have a cloud, again, isolated model, the cloud collapses and just has supernova, you're gonna make too many stars. And I'll agree with that. You can regulate a galaxy with just the supernova because it'll eventually figure itself out where you're balancing roughly the amount of momentum that you need from supernova to balance the galaxy as a whole, but your GMCs will look tragically, catastrophically wrong. And so it's those other prompt processes that are making the GMCs themselves have the few percent star formation rate, because
It depends on those other processes because they clear a path.
how it interacts with that gas. Because yeah, supernova themselves aren't touching gas that's 100 per cc or higher, for instance, or 10 cc per higher even, somewhere around there. But yeah, it's not really affecting the dense gas because that stuff again is separated from the cascade of the ISM writ large.
Can you also mention this ISMs are not very competitive in this feedback? So in that case,
How does this supernova momentum is being modeled? Maybe we can talk it in the private. Yeah.
Yeah, sure.
Next question is like, is this Kennicutt-Schmidt relationship is being satisfied at high redshift fire galaxies too?
By the real universe?
No. In fire galaxies.
Yeah. So for instance, these points, it's redshift, I did 1 to 6, they're all there. And so for us, and again, that was Fire 1, Fire 2, looks pretty much the same. I should really update the plots, it's been years now. But yeah, as a function of redshift, the fire galaxies satisfy, to the best of our knowledge, the observational constraints of Kennicutt-Schmidt.
Okay. And there is no AGN feedback in fire galaxies, but yet we have a massive fire simulations, 6 or 7 times bigger than the Milky Way mass galaxies.
Yes.
Do you think they're accurate in that sense?
I mean, no, because you need AGN at that mass scale for that, but they're accurate in other ways. And so I think those galaxies, I would say the most massive galaxies in the fire box struggle from the sense that if you look at the box, there's like one big filament that those massive galaxies all kind of live on. So I would struggle to say that you should really look at in the firebox, for instance, either the lowest mass galaxies, because we're just running out of mass elements quite soon. They're not very well resolved, and the highest mass ones. And so I would say that you really need to limit yourself to sort of the mid-range of the galaxies in there, where it's L star and below.
Okay, thank you very much.
Quick question, is there any opportunity for cosmic ray pressure and cosmic ray driven winds at any point in future versions?
Yeah, so a lot of people, Phil especially, have been really interested in the cosmic ray feedback physics. And one thing in particular that has really been just like a circular argument amongst people is like in the collaboration is how much it's affecting the CGM and the CGM structure. And so pretty much for the runs that we've seen, either when all the models we've been mostly working with have been cosmic ray diffusion models, and just trying to look at what the diffusion parameter ought to be. Either the diffusion parameter is too low and the cosmic rays never escape the clouds and they essentially don't do anything and act just as an additional, radiation pressure element. Or they're too high and they run away and they don't do anything at all. We've just made our supernova 10% less energetic. But when we kind of have it in that mid-range and the parameter is affecting stuff, seemingly one of the biggest effects that we've seen in our simulations is the structure of the CGM changes fairly dramatically, I would say. So when we don't have the cosmic ray included runs, the CGM is quite hot in our runs. And that's because there needs to be some support out there. And in our runs, given the resolution, it's thermal support primarily in the CGM. Whereas as soon as we put the cosmic rays in and they're actually doing something, the CGM gets a lot colder because necessarily the cosmic rays are doing a lot more of the support. And so that's definitely one aspect of it that I think is interesting, and we're like really interested in the cosmic ray physics. And so if you're a grad student and interested in working on fire, I wouldn't work on cosmic rays.
I have a quick question, if you don't mind. What are you assuming for the clusters in your super bubble model?
Wait, say that again.
What are you assuming for your clusters?
Oh, these clusters. So the mass, I took the scalings from Mike's paper, where Mike had found the cluster formation efficiency scaling with gas surface density. And so the way I kind of closed the loop on this model was I assumed Mike's model of the star cluster formation efficiency in terms of its mass scaled with gas surface density. I said the ISM is close to tumorous stable. Its Q is about 1. So I'm connecting the gas fraction with the surface density and the scale height there. And then the gas fraction basically then goes into the star cluster mass. And then this tells you what fraction of your momentum is going back into the ISM. And so it kind of closes the loop to say how much momentum you get out to balance it to get tumor Q, tells you your star cluster mass. And so rolled into the axes of those plots is like the star cluster mass kind of evolving across it. Yeah.
Gene?
Maybe
Okay, well,
it's
so he asked, does the distribution of dark matter have any effect on the ISM evolving cycle?
I would say, I mean, broadly, yes, in the sense that it adds to the primarily it's setting the rotation curve, which is helping set the scale height. But like self-gravity wise, no, it's not affecting the in the disk, because in the disk, up and down a kiloparsec or so, not a kilometer, a kiloparsec, you're baryon dominated. So at least in the disk, locally, it's not affecting it, but the dynamical time, the turnover time is affected by the global distribution of dark matter. Hopefully that answered your question.
Okay, so that's good.